We're trying to understand matter at its deepest level, and that takes us from the interior of the atom, so the smallest distances really, to the large scale, dark energy and dark matter, which govern the way the universe is put together. The framework within which we carry out that research is called the Standard Model. The approach that we've followed in Adelaide over the last 2 decades is to have fundamental theory, phenomenology, numerical simulation, and very close interaction with experimental physics around the world, all working together in the one place. The Centre for the Subatomic Structure of Matter, or CSSM, was initially funded as an Australian Research Council special research centre to examine the structure of matter at its deepest level and how protons, neutrons, nuclei are composed of quarks.
Most of my research is focused on studying the structure of the proton. The proton itself is made up of 3 quarks, and these are held together by another subatomic particle that we call gluon. Interactions of quarks and gluons are governed by the theory of quantum chromodynamics.
We look around and we think that empty space is empty, but it isn't. It's actually full of quark and gluon field fluctuations. So the very first step in any calculation is to create typical snapshots of empty space. We're doing simulations using not only quantum chromodynamics, or QCD for short, but also quantum electrodynamics. Within the vacuum, there will be areas in which there's a net electric charge, areas of positive charge density and negative charge density, and we'd like to understand how they correlate with the instantons that we see. Only recently has it become possible to do these calculations. It's required decades of algorithm development and even more decades of supercomputer development.
Lattice QCD is a highly competitive field, so there are very limited computing resources worldwide. We team up with international colleagues in the UK, in Germany, Japan and the USA. Being part of an international collaboration allows us to pool together our resources so that we're able to perform simulations that can compete on an international level. We have a very large team of PhD research students who gain access also to these international supercomputing resources, confronting some of the most challenging problems in particle nuclear physics.
In many parts of the world, particle physics and nuclear physics are completely separate and they don't even talk to each other. Here, we work constructively and collaboratively together. And so the students in CoEPP go to the seminars, they meet the visitors who come to CSSM, and vice versa.
CoEPP is a large research organisation funded by the Australian Research Council. It's a so-called Centre of Excellence. The primary area of activity of CoEPP is beyond the standard model of physics. That includes supersymmetry, composite particles, extra dimensions, looking for new particles and new forces, and the search for dark matter itself in underground laboratories. The Stawell Underground Physics Laboratory, so-called SUPL, is a new lab that's being constructed 1 kilometre underground in the Stawell gold mine in Victoria to house the SABRE experiment, which is a direct detection dark matter experiment. Finding of the Higgs Boson in 2012 was the last piece of the jigsaw that completes the puzzle of the Standard Model. The Large Hadron Collider at CERN is made up of a number of experiments, one of which is called ATLAS. We have experimenters here who are part of that program, and they're participating in the search for new physics and other new particles.
Despite being a postdoc here at Adelaide, I'm mostly based in Geneva at CERN. Our main driving force, for us at least, in the experimental group here at Adelaide, is to find supersymmetry. Being a part of the CSSM here and CoEPP has been really invaluable for my own research at least. We get very, very good access to the theory community, so it's been a great opportunity.
There's something very unique about the CSSM CoEPP sort of interface. The CSSM brings non-perturbative physics expertise. CoEPP brings the sort of hadron collider stuff. You really need that conversation and you need the expertise locally to do it. So Adelaide, for me, is by far the best place to be at the moment.
The opportunities, in a sense, for work in CSSM and CoEPP are boundless. We have really outstanding staff.
The ARC Future Fellowship scheme is the sort of most prestigious mid-career researcher scheme. When I arrived, 3 people had already got this in the last 3 years, and there was a record to keep up, and they asked me to apply for this. So, I got their applications and studied how to do it properly, and then got the fellowship, which was great.
We feel that this is an ideal environment for young people to develop into first-rate scientists. We attract really good people to come here for a few weeks, a month, for collaborative research, and we involve our students in that. Quite apart from the opportunities in Australia, many of the graduates have taken senior positions in universities around the world. That ranges from Massey University in New Zealand through to MIT in Boston.
After doing my PhD at Adelaide at the CSSM and CoEPP, I was able to pick where I wanted to go next. Now I'm at the Massachusetts Institute of Technology. Studying at CSSM and CoEPP was really the best possible start to an academic career that I can imagine. I had fantastic mentoring, fantastic teaching, and I was really taught how to be a scientist and how to be a physicist. I really think that the University of Adelaide has a critical mass of top people and that it's poised to be a significant player in the field over the next decades.